No problem.
I'm sorry, can you say that again?
I will interact. Yeah.
All right, thank you. All right, well, welcome everyone to another super happy fun time. I think we have maybe less than 4 lectures. I think maybe we have 3 more lectures and then term is over. Three or 4. We shall find out. Not too many lectures left. So, keeping in line with what what we agreed to a few weeks back, we're gonna try to avoid introducing new things and instead making sure everyone's comfortable with things you've already seen. Okay, so today's topic will be, for example, what was it? Midterm 4 had you talking about linearity and comparability, and so we'll go back to that and still trying to show you some new things, but still going back, not too much. So maybe since this was such a good idea for some people, let's try doing some more graphs right here. So here's some things for you to practice. I think it'll be good to practice these, right? Just to see how good you are at formalizing these things, right? Oh, yes, I can totally do that right here. Let's see. Nope, there. Is that making things bigger for you? Does that help? It's a bit big for me, but all right. If it helps, that's this. Please let me know. All the best, Tammy. So let's try doing a puzzle together. Does anyone see a cycle in this graph? Does anyone see any kind of cycle in this graph? Okay, something nice to warm up with. Five, 4, 3, 2, 1. All right, I'm loving all these replies. That's fantastic. Please keep replying. The answer is no. There's a cycle means you have to start somewhere and then walk in a circle, right? What about right here? Who sees a non-trivial cycle right here? Does anyone see a non-trivial cycle? So there's this one is a cycle right here. You start at 4 and stay at 4. But is there any other interesting cycle besides this one? So many people. I'm really glad you guys are participating. The answer is no. If you notice, this one has everything going down. All right, and so this one is this one will lead us to our final talk of the day, which will be about topological sort. Okay. One more example. What about right here? Does anyone see a non-trivial cycle? So we have a silly cycle right here, another silly one right here, these loops, right, and a final one right here. But does anyone see any other interesting cycles? 5, 4, 3, 2, 1. All right. So yeah, Nishat, you're right. So Nishat says we can start at 0, go to 2, go to 4, and then go back to 0. That's a nice little cycle. All right. All right. Another person says we can do 2, 3, 1. 2 down to 3, down to 1, and then back to 2. Yeah, fantastic. Alrighty. So a moment ago I mentioned this one. I said this one's going to be a bit interesting. I said, hey, it's topological sort, really all of them. But think of the arrows. So someone, was asking, what does it mean? Right? And I only know like 5 of your names, so I'm assuming it was Ayman or Isra or Tamir or someone. So what does it mean? So think of each of these nodes as like a spreadsheet, like an Excel spreadsheet. And each of the nodes is a dependence. Like the cell 2 depends on the cell 4. Like 2 says add up the information in cell 4 and divide it by some other numbers to get the result. Right? And cell 0 depends on cell 4, cell 3, and cell 5. So before I can evaluate cell 0, I have to first evaluate 4, 5, and 3. Okay, so we can think of a graph as a dependence graph, right? So they depend on these things, right? Then one question we can ask is say, all right, how do I now, if this is my dependence graph for my spreadsheet, I have to evaluate the cells in my spreadsheet because I'm going to print it out and send it to someone, for example. Then we need to know how to evaluate the cells. Well, I can't evaluate 0 because 0 depends on 4, 5, and 3. So I should evaluate one of those first. Okay, so to evaluate this one, I have to evaluate something up here first. Okay, let's randomly pick 3. To evaluate 3, I have to evaluate 4 and 5. Okay, let's randomly just pick 4. To evaluate 4, I have to evaluate 2 or 1. Let me just evaluate 1. This one doesn't depend on anything, so I'll evaluate 1. Okay, so when you have a graph, you might be interested in visiting the graph or evaluating nodes of the graph, or you might be interested in doing stuff to the nodes of the graph one at a time, like in linear order. You want to pretend your graph was a sequence, right? And the way to do that is called topological sort, and we'll build our way up there. Okay, ducks. All right. So let's. So again, I recommend please try to do these, right, and make use of course help if need be. But you want to be comfortable doing these kind of things before the exam, ideally. All right. So this little talk about you have cells in a spreadsheet and you want to evaluate them, but they depend on other cells, so you have to evaluate the other cells first before you can evaluate the lower ones. That's the motivation for topological sort, and we'll get back to it briefly at the end. But please look at LADAM 14.4. It uses the same motivation about spreadsheets and cells, and it's very accessible. It's 2 pages, right? 1 page for the simple algorithm, and then another page for the complex algorithm. And the reason we've chosen to do topological sort instead of any of the other algorithms available for graph theory is because it's not too difficult. And it also builds on the idea of linearity, which you already saw back in midterm 4. So trying to build on the same things. We're working with sequences, so this algorithm doesn't introduce anything new, right? You've seen sequences, you've seen orders, you've seen linearity, you've seen graphs. Now we're just saying, how do we connect all of them together to get something like this, right? So last time we talked about, I showed you this slide on inductively defined data types. So let me, since this is so very huge, I'll just write here. So I'll just write in Haskell. So we had the natural numbers, right? Sorry. We had the natural numbers, and we said the natural numbers are either 0 or they're the successor of another natural number. Okay, so these things are just, a successor, 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 successor of 0. They don't contain any information, right? So you can think of these as long lists without a payload. Okay, then we said, all right, what if we instead have a sequence where the elements are drawn from some type tau? Okay, then this sequence can be empty. It can be empty, or it could be a value from tau, right, followed by another sequence. Okay, so this is a list with payload type tau. Ooh. Okay, now we're going to change up a little bit more, and we're going to say, all right, what if you have a tree, right? So you have a binary tree, right? A binary tree of type tau. Now this tree could be empty like this, a triangle like that, or it could be, let me just show you the notation we'll use in this class. So this is the notation we'll use. No, I can't copy paste. That's super unfortunate. But so here's the syntax we're going to be using for these kind of trees, right? And in a moment I'll explain why we use these funky names. So B tree. Okay. So before you've seen O plus, right, to denote an arbitrary position. Now we're using triangle plus, okay? So if you notice the structure between them, they're very, very similar, right? So this is now, it's kind of like a list. It's graphs with two children and payloads of type tau. How do you spell the word payloads? Okay. So notice the similarity here, right? The similarity is when we talk about the natural numbers, there's an empty or zero natural number. Sequences, there's an empty or a 0, 1. For binary trees, we're just going to call it this triangle, right? Just triangle plus, just to denote an empty one, right? At first, we thought about just reusing epsilon, and then we're like, let's give them a new name just to avoid confusion. A lot of places would just use epsilon as well. And here we had, you give me a value, and then there's a pointer, right, or an arrow to the rest of the graph, right? So this one is a boring line, right? This is a linear graph. I have either empty, or I have a value, and then another one, a value, and another one, a value, and another one. Down here, we have empty, or I have a value, and I slide down to the left, or I slide down to the right, okay? And here's more, like if you see it as a graph, I have a value 7, and then I can slide down to the left, and I have another graph, or I can slide down to the right, and here's another graph, okay? And the symbolic names are to remind you of this idea of pointers, right? When you have an implementation, you actually have a pointer to another data structure, right? But if you're not comfortable with the implementation, okay. But I just wanted to just show you this idea, all right? So they're very similar, and just as we did induction here, right? Every natural number is either 0 or of the shape successor of another number. Every sequence is either empty or it's the cons of another sequence with a value. Every tree is either empty or it's the branch of a value and two children trees. Okay, so everything we've done before, natural numbers, sequences, now also applies to trees. We can do induction, we can do recursion, so we can do pattern matching, right? So similar ideas apply. Alrighty. And the cool thing we noticed was, hey, trees are well-behaved graphs. They're connected, they're directed, and they're acyclic. Okay, the trees are always pointing down, and they're always connected. This one is not connected. Does anyone know why this one's not connected? 5, 4, 3, 2, 1. It's not connected because of our beloved 6. 6 is forever alone. So this graph is not connected. Okay, yeah, silly 6. All super sad. 6 again here makes it not connected. But here, 6 has a lot of friends. It's 5 that's forever alone. And so this one's not connected. So none of these are trees. Okay, none of these are trees. Another aspect of a tree besides being connected is depending on what kind of tree you're talking about. Most often we're talking about binary trees, but there's also, of course, arbitrary branching trees, also known as rows trees. This is a tree where you have a value, for example, an integer, and you can have as many children as you want. So here's 7, and 7 has 3 children. Okay, so so again, none of these are trees, okay? Because you can have as many children as you want, but each child has one parent. So here, 6 has a lot of parents. 6 was raised by a village. 6 has, 0 to 4 as parents, all right? 4 has itself as a parent and also has 2 and 1 as parents, okay? So there's other reasons besides being not connected to dismiss a graph from being a tree. Right? You have to be connected, you have to be directed, and lastly, every tree can have at most 2 parents, 2 children, and they have to be disjoint. Okay, so that last part is called being acyclic. Okay, so I have to be acyclic. There's no way for me to reach a node from 2 different paths. Right? So another way to say it is every node in a tree is uniquely accessible from the root node. Okay, so to get to 5, there's a unique path to get to it from 7. Namely, I go left, then I go right, and I can get all the way to 5. All right, so there's no diamonds or circles. All right, okay, all right. So we're just going to focus on these kind of trees, and because we've been using Unicode all along, we're going to avoid the name empty and the word branch. Instead, we're focusing on triangle plus and this branching, left branch, then the element, then the right branch. So right here we have 7 is the main node, right? That's right here, 7. And then you slide to the left to this smaller tree and slide to the right to this other tree. Okay. Now this other tree has main node being 10, so 10. And if you try to slide to the left, there's an empty tree right here. It's invisible, empty. Okay, that's what that is, empty tree. We don't draw it. And then if you slide to the right, you get 11. And 11 has no right and no left child. That's what the empty trees are used for. Okay, so think of a sequence. A sequence is you have a value and then you point to another one, then you point. So you have just a bunch of points down. That's a list. The list is I have a value, then you can go down to get to the next value, then down to get to the next value. But a tree says you don't just go down, you can go down left or go down right. Okay? And a branching tree says you don't just go down left or go down right. A branching tree says you can go down left, you can go down to index 0, 1, 2, 3, as many indices as possible. Okay? So that's the difference there. And as before, we can do tree induction, right? Just as we did here, to do induction over n, you consider the possible shapes, right? To do induction over sequences, you consider the possible shapes. For trees, you consider the possible shapes. To prove a property P is true for all possible trees, well, how is a tree made? A tree could be empty, okay, then I have to prove the property directly. Or a tree could be formed by a branch. If a tree is formed by a branch, that means it's formed from a left tree and a right tree and then a value node, a payoff or a payload. But if I want to prove the property is true for a branching, I just need to make sure it's true for the left tree and for the right tree. Okay. Notice this induction principle is almost exactly the same as the induction principle for sequences, right? For sequences, we only had a right child. Every time you go right, you go right, you go right, you go right. There was never a left option. So if you just cross out the left and you cross out the left, it will look almost exactly like a cons. So let me try to do that, and maybe I will convince you. So suppose there is no left. Let's get rid of that. There is no left. Get rid of that. And right here, there is no left. Okay. Now it looks like I'm just doing X cons R, right? So trees really do generalize sequences, right? This really is a increasing generality. This has no payload. This has a payload. This has multiple branches, 2. Okay. We're not gonna show you we're not gonna work with this one that has arbitrary branches, just because it's a bit harder to work with. But it's also a bit elegant, depending on who you ask. Okay. So are there any questions or concerns there? And just to remind you, this is the real language. This is called Haskell, right? And you can declare it like this in Haskell. So the knowledge you're learning right now by declaring things in CalcCheck almost readily applies to working in other languages like Agda or F#, right, in the Microsoft .NET framework, or Haskell, right, or OCaml or ML or SML, right? So I just want to let you know these things are you'll get more comfortable doing functional programming, hopefully. So here's a little operation on trees. It's called mirror. If you remember you had a sequence and you could reverse the sequence, right? Haskell B curry. Yeah, curry, delicious stuff. So remember how you had a sequence and you could reverse a sequence, right? Because there's a payload, you change the order of the payloads. But for numbers, you can't reverse a number. There's just a bunch of successors and then a 0. All right, you change the s's around. There's no payload to make that distinguishable. But when there's sequences, you can change the payload, right? It's 1, then 2, then 3. Okay, change them. So it's 3, 2, 1. Read them backwards. But for a binary tree, every tree has a left and a right child. So now instead of left and right, flip them. So now it's right and left. And when you flip them, this is called a mirror operation. Okay, and of course, because trees generalize sequences, when you flatten a tree down, you get a sequence. And then if you decide to reverse your sequence after flattening your tree, that's the same thing as mirroring the tree and then flattening. So you'll see some stuff like that right here. Okay, so here are some operations for you. So to mirror the empty tree, you leave it alone. To mirror a branch with a left and a right, you just flip the right and the left, and then mirror each of those recursively. This is very much like how reverse was defined. And we're going to use the notation of converse just to get you comfortable with seeing converse operations besides relational converse. Okay. If a tree has only one thing in it and you try to mirror it, okay, it's the same tree. There's only one value there. Okay. And so this is the example that I wanted to show you. So in this example, right, we're trying to show that for every tree, if I mirror the tree and then I mirror it back, I get the original tree, right? So I have to first, I can use induction. Induction says tree and show it for the branching, assuming you have it for the children trees, right? So for the, so let's just do this together. Let's just start off together, okay? So we're using tree induction. That means we need two subproofs. Subproof, and we need another one. Okay, so we need two subproofs. The first subproof says we need to prove this is true for the case that T is the empty tree. All right, so let's write that down. Subproof for this one, empty tree, and right here. Okay. All right. Now, by definition, right, recall how mirroring works on the empty tree. It takes the empty tree and leaves it alone. So we can finish this in one step. We can just say by the definition of mirror. Okay. And that should discharge the first step. And there we go. That's good to go. All right. So what do we need to prove in the second one? Does anyone know? All right. So what do we need to prove down here? Let's have an interactive proof. What should go down here? We're having a subproof for what goes here, guys. So here's the induction principle. All right. Give you some guidance. What should go here? We need to prove this thing. Yeah, so we need to put in this monster right here. It looks super scary. Let's bring it all the way up here. And what's our P every time? Our P every time is going to be this thing. All right. So we put that in there, but instead of this, we have L. Okay. And we have it again with R. And then finally, we have it with the branch. All right. So if I have a branch and I mirror it, and then I mirror it one more time, I should have the branch. L. Oh. Okay. So this is what we need to prove. All right. It looks I put in the new lines because I've zoomed in for you. Okay. Actually, let's just use the full screen. Silly that we aren't using the full screen. Okay. So here's the full screen. All right. Boop. Even bigger. Okay. So now, how do we begin our subproof? Who knows what do we do next? How do we prove something like this? How do we prove a for all statement? To prove a for all statement, we use the keyword for any. So for any L, R, and X, we make some progress. Okay. So now that we put in a for any, what's the next thing to do? Come on, guys. What are we doing next? So the for any gets rid of the for all part, and now we need to prove this part. Okay. Exactly. When you have an implication, you're using a assuming clause. So we're assuming these two pieces. Everything before the implication is what we get to assume. Let's do that. Okay. Let's give them names so it's easier to refer to them. So let's call the second one, let's call it R, assumption R, and let's call the first one assumption L. Okay, just so that we have names to refer to these assumptions. Right? And you can see the names right here. L is the first assumption and R is the second assumption. Now what do we need to do? We need to prove this thing. How do we prove that? How do we prove an equation is true? All right. All right. Do we take the whole thing and turn it to true? Is that what we should try? What should we do? This is practice for the exam, right? You know, like having a dialogue, a conversation. You try, right? You know, grab a paper and a pencil, and then, you know, this is to help you out, right? I can just show you some boring slides, but you know. All right, excellent. Let's start off. So almost always, you don't want to take the whole thing to true. So someone said that. Almost always never take the whole thing to true. If you try to take the whole thing to true, it will probably just be really long, and it will probably require a lot of copy pasting, and it might mess up your calculation. So when you're super lost, maybe do the whole thing. But rule of thumb, here's what you're trying to prove, and you don't know what to do. Well, it's an equality. And so an equality means you can transform one side to the other side. Now, which side should you pick? If you're super lost and don't know what to do, pick the side that has more symbols. So this side has 2 more symbols than that side. So let's start with this side. Okay. So there's just some simple rules of thumb. Okay. So we'll start here because it has more symbols. Okay. So we'll put that in there. Okay, so now somebody tell me the holes. I'll do it, and you tell me the holes. What did I do? What have I done? How did I move this first step? What did I do right here? Okay, so what are the holes here? So the first one is mirror, right? That's fantastic. What about the second hole? Right. So I apply mirror one time to bring in the first one. Then I mirror again to bring in the second one, right? And so I have each subpart mirrored twice, right? And notice the first mirror moved R to the left side and moved L to the right side, but the second mirror brought them back to their right positions. Okay, so going to the exam, you really want to be comfortable doing something like this, a single step, just to save you time and space. That's all. All right, fantastic, good. And now someone says, let's just do assumption L and assumption R. Okay, and we're done. right? So that wasn't too hard, hopefully. Somebody says, can we use self-inverse of converse? That's exactly what we're proving, though. We're proving self-inverse of converse. Okay, so we're using the same notation just to remind you of it. But notice this notation is called mirror, right? We declared it right here. We're overloading. We're using the same name, right? For relations, this is called converse, but for sequences, it's called reverse, and for trees, it's called mirror, right? And it behaves the same across all three data structures. Okay, so when we've defined it, and now we're proving that it satisfies the same properties we're accustomed to. In particular, one of the properties you expect of a reverse operation is that it undoes itself. So that's exactly what we're proving. So good question, Jishan. Right? Okay. Now, what if I try to do this? Will this work? All right, who knows? All right. That worked. Okay, so you can always try these things out. What if I tried to do this? By that almost worked. Did not. Okay, there you go. So that worked. How do you feel about this proof? Who likes this proof? What if we did this? You do? Okay, what about this? What if I this line is really long. It's a really long line, and you know what to do. You see tree induction right here. So having to copy paste this is a waste of time, really. And you're in an exam, you're in a rush. You don't want to write this down, do you? You know what to do. If you do, you can just get rid of this. Okay, let's check that. Oh, it doesn't know the types anymore. Okay, so we need to actually mention the types. So it doesn't know what the types are. So we needed it here. That was unfortunate. My Control Z didn't work. No. All right. So I was just trying to show you some of these, but some of them will not work. So this one you can definitely do. Yes. Alrighty then. So it couldn't figure out the goal, unfortunately. So if you can't figure out the goal, you have to write explicitly. All right. And just as before with trees, we can define things by looking at the shape. I have the size of a tree. If it's empty, the size is 0. If it's a branch, let me get the size of the left, the size of the right, and I already have 1 because I see a branch right here. All right. Just as we did with mirror up here. Okay. So let me go back right here. Okay. So just in case you've forgotten, induction says to prove a property, right? I want it to be true. I need to make sure I start off true, right? And every construction, like my branch, takes true. It takes things that satisfy that property, and it preserves that property. It preserves the P property, right? You know, if L has P and R has P, then the branching also has property P. Okay, you know, if my left branch is green and my right branch is green, then when I make a new tree, the whole thing is green, right? So my constructions preserve greenness, right? If I was interested in the property green, okay. So again, this is from chapter 12. So let's look at it just a bit slowly. We said that a relationship is well-founded when there is no infinite descending chain. That is, you can't look for smaller, 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 smaller. Eventually, you just stop. All right. So to prove a property is true, right? You say, all right, I just need to show that the property is true, assuming it's true for everything smaller, okay? And it's well-founded means the list of things smaller eventually terminates. It's not infinite. At one point, there's a smallest thing. Then this is what I can do. To prove a property, I can give it a stronger assumption. I can say, hey, as I prove my property P, I am allowed to assume that the property already holds for smaller constructions. Okay? So here for trees, when we talk about smaller, we say, all right, what does it mean for two trees to be smaller? Is a tree smaller than the empty tree? No, there's nothing smaller than the empty tree, so that's false. If I have a tree, when is it smaller than a branch? It's smaller than the branch when it's the left part of the branch or the right part of the branch, right? So what we're saying here is this is called being a subtree. So for example, the tree 325 is a subtree of the bigger tree. Let me just draw two. So here's one tree, and here's a bigger tree. Okay. So this is like being a sub-expression, right? Being a subtree is almost exactly like being a sub-expression, because trees and expressions are the same. Okay, as I keep repeating, like a broken record. So I hope to have convinced you some of these. So here's my big tree up here. Here's a smaller tree, and this part is even smaller. Okay, and now that I've gotten to 2, the only thing smaller than 2 is the empty tree, and then there's nothing smaller than the empty tree. Okay, and so now theorem 219 says to prove a property is true, you can assume, as you try to prove this property, that it's true for everything smaller. Okay, but in this case, everything smaller, well, when x is the empty tree, there's nothing smaller, so I have no assumptions. And when x is a branch, then my definition right here tells me the only things smaller are the left and the right. And so that's the second assumption of the inductive step. Okay. Does anyone have any questions here before we move on? It's all good? So trees and structural induction are just absurdly important in computer science. Graphs are really important as well, but induction shows up so often. Because everything we write down in English or in any language, how do you write something down? Either you write nothing, that's the empty string, or you write one word followed by another sentence. Okay, so the way to write sentences is inductively defined, either the empty sentence, 0 words, or a sentence that has one word followed by another sentence. Okay, so everything you decide to write down is always empty, or it has a word followed by more words. And so everything you write down is a sequence, right? And so whenever you want to argue about statements in a language, you're talking about sentences. Whenever you're arguing about the shape of a program, you're talking about sentences again. When you're talking about the English language, talking about sentences. When you're talking about expressions, those are particular kinds of sentences, right? Trees are sentences that are parenthesized, right? So almost everything is a tree or an expression or a sentence. So they're just so natural. They're so ubiquitous. They're just literally everywhere. You just notice, wait a minute, this thing is always composed of smaller pieces. That's a tree. Right? So they're literally everywhere. Induction, amen, and recursion are almost exactly the same thing. So remember, I keep saying programming equals proving, proving equals programming. Induction, recursion are almost exactly the same. And in other languages, there is no difference between the two. Right? So in some languages like Agda, you can't differentiate between induction and recursion. They really are the same. You cannot make a difference between them. Right? They're the same thing. Right? So until you get to esoteric notions of induction and recursion. Okay, next. So here's another example that you can try to do your own, right? But the idea, the main principle stays the same. So we define a new data type, right? It's called a Huffman tree, right? It has a branch on the left and a branch on the right. And notice, there are no empty branches anymore. Now there's leaves. Instead of an empty branch, you have a leaf. Every circle has a value inside it, okay? And you can declare this in Haskell, right? Or you could declare it in CalcCheck. In CalcCheck, you say, I have a leaf constructor. Every value A gives me a tree. And I have a branching constructor, which has a left tree and a right tree, okay? And then I can just use it like that. And the important thing is you have this induction, which says, hey, to prove a property about these kind of trees, I prove it for the singleton trees, and then for any branch, I prove it for the left and the right. I assume I have it for both of them, okay? And then you can define a notion of mirror for these kind of trees and prove it similarly, right? The important thing we're trying to teach you here is you can make these inductive data types, and when you make them, they come with recursion, which is how you define things, and they come with induction, which is how you prove things. And they happen to be the same, induction, recursion, right? Programming people will say, oh, it's called recursion. Math people will say, oh, it's called induction. And you people who know that programming and proving are the same thing will say, they're the same thing, no big deal. All right, so the idea is you define stuff and you can get interesting things interesting principles out of them. Okay. So hopefully this is not this is what we're trying to get you to see, how to see that, hey, whenever I make a compound structure, if my compound structure has for it to admit induction means I prove a property about my compound structure by looking at the smallest possible structures, and then for any variant of them. So let's try that. Let's try one together. So let's try one together. I'll leave this here for you. Let's try one together. Let's try one called data. We're in core 2, so let's try data C2, and it has a data type, and here's what it can have. It can have EPS, or it can have just, or it can have more, right? And how does more work? More takes a value, and then it takes a C2 and another value, okay? Actually, let's give this a strange name. Let's call it arrow, okay? So here's our 3 ways, all right? So a C2 can be an EPS, it can be a just, or it can be an arrow, okay? So what is the induction principle for this data type? Let's try to do this together. What is the induction principle for C2? Let's first learn how to spell the word induction. Okay, so who wants to start us off? How do we prove induction for this one? All right. What is the induction rule? So we want to show for all C of type C2, I want to have a property P is going to be true. Okay. So to show that P is going to be true, I need to show, somebody says, let's examine the shape, right? So we need P with C being EPS, good. What else do we need? What else do we need? So to prove this property P is true, you investigate the shape of C. C could be EPS, it could be just a value, or it could be a value and then an arrow pointing to another value. So the next one we need to show, that for all possible values of type tau, that P with C being just X is going to be true. Excellent. And then one more. Okay, what's the last one? Okay, we can do this, guys. We can do it. We can do it. What's the last one, right? So a C2 value can be EPS, or it can be a just. And the last one is an arrow construction. So notice, the last one can be for all x of type tau, and I have a child. So, and my child is to the right, so let's call it R. And I have a C2 of type tau. Forgot to put the tau right here. Here's what I'm going to have. I assume the property is true for the child, so C becomes the right child. And using this assumption, I will now show that the property is true for X pointing to the right child. Okay, so to prove a property is true for C2 means I first, what is the possible shape of C? Well, C could be EPS, or C could be a just X, where X is a value of type tau, or C could be an arrow pointing to a right child, right? So let's look at some. Here's some values of C2. For example, of C2 natural numbers. So here's a value. 0 points to 11, points to 3, points to just 4. Okay, so that's one. Here's another one. Just EPS. Here's another one. Just 5. And here's one more. 98 points to EPS. Okay. So I chose the name arrow because these look like sequences, and sequences are just particular kinds of graphs, right? But a sequence has a cons construction and an empty, and now we threw in a leaf or a singleton list in there as well, okay? And you came up with the induction rule, so good job, okay? Can we have 98 to just 5? Yeah. So look right here. This is a value right there, 3 to just 4. All right, so also 98 to just 2. Okay, so these are all values of this new type. Okay, good job, good questions. Okay, so so we talked about symmetric closure last time, right? We also talked about reflexive closure. We talked about closures in general. Closures are what you add in to get a new property, okay? Then we talked about reachability via transitive closure. Then we said, what if I want to make 0 steps? That was reflexive transitive closure. Right? Somebody's asking right here, this is supposed to be an AND, because remember, a for all means a bunch of ANDs. So C could be empty, and C could be a just, and C could be an arrow construction. So that's why this is a for. Remember, a for all expands into a number of ands. Okay, ducks. Good question, Jishan. So we talked about arbitrary closures, right? I gave you a little look here somewhere about these as well. We said here's another way to look at these kinds of closures. We did a little bit of a pseudo argument yesterday. And what I wanted to get to today was kernels, right? So a closure is add in enough to get a new property. Kernel is what's the biggest part that has the property. So since we've run out of time, we'll come back to it. But I just want to mention that we talked about topological sort at the very beginning. You have a bunch of things you want to evaluate, and you want to pick, do I evaluate them in this order? Do I evaluate them in that order? Which way do I evaluate them? And the way to get this evaluation is called topological sort. To pick this linear order is called topological sort. So we'll get back to it on tomorrow. We'll review some of these that I went over really quickly tomorrow. But please look in the book for topological sort, chapter 14, and we'll continue from there. I hope you're learning a lot of cool stuff, and I'll see you tomorrow. I will be here afterwards in case anyone has more questions. And everyone else, have